This is Ochem Chapter 10 review. It's the last chapter of the semester, and it really focuses on radicals and radical reactions. So we're just going to get into it. Question 1 asks, a free radical can be produced by what? Well, whenever you do these types of problems, you typically see an arrow like this, and it has some halogen, let's say Br2, is what you're mainly going to be working with in this chapter, reacting with light, and we call light HV, right? And you can react it at a very high temperature, like 400 degrees Celsius. That's pretty typical for these types of reactions. So what I'm saying is that you need high temperatures. You can do it with light, and if you don't have anything like this, let's say that you're already doing a reaction and it's like halfway through the reaction you see something like CH3 with like a little electron plus Br electron. Well, those two molecules, those radicals, can actually combine to make a product. And so the reaction of a molecule with another free radical. So this could happen, or you could just have CH3 plus Br electron. You could do that as well. Okay, so for these types of reactions, you need some high temperatures. If you don't have high temperatures, you can do it with light reaction. And if you don't have either of those, you can just have two radicals, right? And they can just combine or do their own thing. So that was that. Let's move on to question 2. The term peroxide used in chapter 10 refers to what kind of structure? Well, it could be actually all of them, right? All of these are pretty good. So the common designation, like the notation for peroxides, are like this: ROO R. And if you want to see it in a Lewis structure, it looks like R, and then it kind of goes to an O, O, and R, okay? Or let me do it better. O, O, R. Okay, so these R's, it could be, R, O, O, H, or these R's can be halogens, or that H could be a bromine. It doesn't matter, okay? You just need to have like two oxygens next to each other, and you're gonna have your R groups. Now these R groups can be bromides, chlorides, hydrogens, etc. It just has to follow these types of structures. So ROOR is very stereotypical peroxide. It's very common. In this one, they swapped out the R for the H for the hydrogen. That's perfectly legal. You can do that. Over here, they have a lot of stuff going on, but you still have this kind of like the foundation right here. So we have RCOOCR, right? So it's the same thing. Just in this case, the carbons right here, imagine that they were R's, okay? So it would still be ROOR, right? So it's just kind of like the notation for peroxides, okay? So D would be all of the above, and this is E once again, right? So that's just kind of like the common formula for peroxides. That's all, nothing fancy. Which of the molecules is not expected to arise as a product for a high temperature? So whenever I see high temperature, I'm thinking like 400 degrees Celsius, or it could be like 4 million degrees, to be silly or something. 4 million degrees Celsius. Chlorination of methane. Okay, so let's say that we have methane, right? So CH3, actually CH4, sorry. So let's do this. CH4 plus chlorination. So we're going to put Cl2 at like 400 degrees. So what could be a product? Okay, let's erase everything over here. What we do here is that we just write out the methane, right? And we can remove a hydrogen, right? So if we remove one hydrogen and replace it with a chlorine, this is a possible product. That's a possible product, and it's kind of bothering me right there. So let's do this. Yeah, so that's a product right there. And let's see, we can do it again. We can do C, chlorine, chlorine, H, H. And so you can already see what I'm going to do. We can do this again, and we can have 3 chlorines. And we can also have 4 chlorines. Because chlorine in this case is not picky. It's very open for reactions. Like, it's not picky at all, okay? It'll do a lot of stuff if you don't keep it in check. And what I'm trying to say here is that just because you have 2 chlorines doesn't mean, oh, my answer should only have 2 chlorines. No, for some reason. Well, not for some reason, but just because you have Cl2 doesn't mean you only have 2 chlorines, okay? Let's imagine that you have a whole gallon of chlorine. You have like a cajillion chlorines floating around, okay? So that's where these guys pop up, right? So, oh, that's Cl2? Well, you also have another chlorine, right? Because you have trillions and trillions of atoms, of molecules, right? Of chlorine. So what I'm saying here is that chlorine is not picky. If you heat it up very high, like 400 degrees Celsius, you can have 1 chlorine, 2 chlorines, 3 of them, and even 4 of them. So at high temperatures, chlorine can take over the molecule. So that's 4 of them. You got 3 over here. You got 2 chlorines. You also have CH3, CH3. Well, yeah, you know, this could happen, but that's not really easily seen, right? It's not intuitive. But E, notice E can never happen. Why can E never happen? Well, E has a double bond. And do we form double bonds when we're doing radical reactions? No, we don't form double bonds. So you could say no alkenes, with, you know, radicals, right? So whenever you're doing a radical reaction, there are no alkenes, all right? So A, B, and C, they're incorrect because they can happen. D can also happen. You can have, you know, a methyl, right, reacting with another methyl, and those can link up, and you can get like this weird hybrid CH3, CH3. Yeah, it's not gonna happen a lot, but it's possible. So those are just, radicals. And if you don't know what a radical is, it's just a lone electron. Okay. Hopefully that helps you out. Now we move on to number 4. All right. So this was E. Number 4 says, which of the following gas phase reactions is a possible, that means it can happen, chain terminating step in the light initiated chlorination of methane? So this portion right here, it could scare you, so don't pay attention to it. All the question is asking you is, what is a terminating step? So a terminating step is always when 2 radicals connect, right? When 2 little electrons connect, you don't have any more radicals. And if I don't have any more radicals, my process ends, right? My train stops. So, you know, you can think of this as a kind of like a train carriage, right? So when you see of like the old Western trains, you have a lot of cabooses. Okay, well, each individual caboose is like an electron. Okay, it's like a radical. They can connect, they can disconnect, they could go to different trains, they can make a train longer or shorter, right? But if I connect 2 cabooses together, well, you know, they don't have any more freedom. They're linked up. They can't move around. Likewise, these electrons, these radicals, I might add, these radicals, if they connect by themselves, well, you know, I ended the process. This can't connect to any more molecules. So when 2 radicals collide, the termination is complete, okay? So what am I saying here? We have a train, a molecule. It separates into 2 cabooses. Well, those cabooses can go to other trains. They could do other reactions. So that's not right. Right here we have a caboose, and then we also have a train. They connect, and then you also have one caboose, right? If you don't like that analogy, I'll stop. So what I'm saying here is we have a radical, we have a methane, in the end we have a radical. If you have a radical as a product, we can still continue the reaction, so that's not good. Over here we have two radicals, notice the dot. If these two radicals collide, then I'm not going to have any more reaction. So if my product doesn't give me a radical, it was terminated. For C, for answer choice C, my product does not have a radical. So it was terminated. So C is going to be the correct answer, okay? D has a radical, and then in the end, I also get another radical. Well, that means I could do another reaction. So my process was not terminated. It's wrong. So as a recap, it should be C, but as a recap, if you have a radical going in and no radicals coming out, that was a termination. If you have no radicals going in and a radical coming out, that is initiation. If you have a radical going in and then another radical going out as a product, that is propagation. That means it just means a fancy way to say continuing. Okay, so it's a continuing reaction. In the presence of light, ethane, 1 mole, reacts with chlorine, 1 mole, to form which product or products? Well, first off, I don't like how it says mole or mole, right? I don't like that because it's really confusing and it makes the answer not intuitive. Like, oh, why would that be the correct answer? Well, it's easier if you ignore the moles, all right? So just pretend that we're reacting ethane with chlorine, okay? So ethane with chlorine, let's do CH3. And we're reacting it with chlorine. And let's say it's at 400 degrees Celsius. And we're reacting with light as well, okay, because it has the presence of light. Okay, so HV. Okay, so again, it's easier when you ignore the moles. Like in question 3, I believe it was. Remember that this whole thing, this whole molecule, can be chlorinated. So everywhere that you see an H, you can make a chlorine, right? So if I wanted to, I could be extreme and I could just remove all the H's and replace them with Cl. So I could have a Cl here, 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 all at once, right? So let's draw this out. CH2 with a chlorine. You can also have a carbon with a hydrogen and then some chlorines. So again, they just replaced this, and this with chlorines, okay? CH3 means I kept this the same, and I changed these two to chlorines, which is possible. CH3 means that this stays the same. CH2 means that stays the same, but I replaced this with the chlorine. And you see what's happening, right? They're just randomly taking out a hydrogen and putting in a chlorine. That's totally legal to do. There are no double bonds being made, so that's pretty good. What about the last one? We have a Cl and a carbon with 2 hydrogens. That means they changed that hydrogen. Again, I'm just circling these hydrogens randomly. It could have been this one, or it could have been that one, okay? It doesn't matter. Let's say it was this one. Then CH2 with a chlorine. Okay, well that's perfectly legal, right? They replaced it. They replaced a hydrogen with a chlorine, and then they placed another hydrogen with a chlorine. Now you're probably wondering, oh, by the way, it's E, so all of these are possible. You're probably wondering, okay, that makes sense. I have 2 chlorines to begin with. I have 2 chlorines here. I have 1 chlorine here, that's possible. And over here I have 2 chlorines. But over here, I have 3. Where did that third one come from? Well, that's what I'm saying when I tell you to ignore the moles, right? When I tell you to ignore the moles, I'm telling you, hey, you actually have more than 2 chlorines, okay? You have a mole of chlorine, right? It's weird. Just always assume that you're not working with just 2 of them. Assume that you're working with an infinite amount of chlorines, okay? An infinite amount, right? That's the easiest way that I can tell you, because if you don't assume that you're working with an infinite amount, you would mark A as incorrect, because that's 3 chlorines. We only have 2. Well, that's wrong. Assume that you're working with an infinite amount of chlorines, and that chlorine can take off as many hydrogens as it wants, as few as it wants. It doesn't matter the location. It could be random because it's not picky, okay? That's why we don't really work with chlorine. It's not picky. We can't predict the product. Some products are better than others, and so we don't work with chlorine. We really work with bromine, okay? So as a recap, ignore the moles. Assume that you're working with an infinite amount of chlorines, and those chlorines can rip off any hydrogen that it wants and place itself in that location. Okay, so it's E, all of these choices. In a competition reaction, equal amounts of 5 alkanes compete for a deficiency of chlorine at 300 degrees Celsius. The greatest amount of reaction would occur in the case of which of these alkanes. So it's asking me, hey, which one of these molecules has the most chance of reacting with chlorine radicals? Okay, well, let's draw it out. Ethane, that's just a line. Propane, well, it's a line because, you know, that's 1 carbon and that's 1 carbon. 2 carbons is an ethane, okay? So, hold on. Oh. This is great. Anyways, propane is 1, 2, 3. Butane is 1, 2, 3, 4. Isobutane is a Y shape. Butane is just 4. 1, 2, 3, 4. 1, 2, 3, and 4. Okay. And pentane is 1, 2, 3, 4, 5. So which one is going to be more reactive towards chlorine? Well, in the case of ethane, if I have a radical right here, that's not good, okay? I'll show you. The trend for radicals is that a tertiary radical is better than a secondary, is better than a primary, okay? And what's better than a tertiary? An allylic, okay? So if I have something like this, right? This is allylic, okay? This carbon right here, this carbon has a double bond on it, okay? So I'm not gonna make a radical over here. That's bad. Instead, I'm gonna go to the neighbor carbon, okay? So it's like the one that is next to the double bond, right? It's weird. It's a weird concept, but just notice that you want to get away from this double bond, right? So go to the carbon that doesn't have a double bond, okay? So it's going to be this one, not this one. That's bad, okay? Allylic, which is what I'm drawing right here, is this guy, okay? It's the carbon next to the double bond, okay? Now a tertiary is going to be like this. That's a tertiary. That's really good. It's like the best one if you don't have allylic. A secondary is this guy. And a primary is this guy. Okay? So you can see what happened. Ethane is pretty bad. Here's ethane. If we put a radical right there, that's going to be really weak. And it's not good. Okay? So that's bad. That's going to be a primary. That's bad. Okay, what about propane? Well, if I put it here, that's a primary. That's bad. What if I put them in the center? Then I get a secondary radical. But that's not too good, right? I mean, it's not good. It's better than a primary, but it's worse than a tertiary. Alright, what about butane? Well, if I put it here, I get a primary. That's bad. Secondary, 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 right? Which is not good. And by the way, if this isn't making sense to you, I'm saying secondary. You can think of it as like this. Okay, well, how many carbons are connected to that radical? 1, 2. Okay, so it's secondary, right? Over here, if I put it here, how many carbons are connected to it? 1. That's a primary, all right? So butane only gives me primary or secondary. What about isobutane? Okay, well, if I put it here, I get a primary. If I put it here, I get a primary and another primary. Okay, but what if I put it in this carbon? Well, I get a 1, 2, 3. I get a tertiary radical. And tertiary, according to my chart, is really good. Okay, it's really good. What about pentane? Actually, it's not butane. Butane's 4, 1, 2, 3, 4. My bad, that was pentane. Sorry. Well, again, that would just be primary and secondaries. And so isobutane, D, would be the best molecule to be reacting with because it gives us a tertiary radical, okay? So again, allylic, which is this, is better than a tertiary, that's better than a secondary, and that it's better than a primary radical, okay? When you're working with bromine, this is going to be very important, okay? I'm going to tell you up front for this question number 7 that my bromine is always going to pick the tertiary carbon, okay? So think of carbon cations, right? You always want it to have a plus charge on the tertiary carbon, right? Well, it's the same concept, except with bromine and radicals, okay? So that means that I'm not going to be reacting here or there because those are secondary spots, okay? And I'm not going to be reacting over here because that would be a primary spot, okay? It's like saying you have a bromine right there. It's attached to one carbon. That's not good. So where can I react it? Well, let's do it. Over here we have 1, 2, 3 carbons. That means if I put a radical right here, I get a tertiary radical, right? Okay, so my tertiary radical is right there. It can attach to this bromine. So let's do the arrow pushing, right? Okay, so let's say we have a radical right there. Actually, yeah, so let's say there's a radical right here. And we have a bromine and another bromine. One breaks off. Notice that I only did a single head arrow. This is what you see right there. That just means that only one electron moved. Okay. Let's do that better. All right. And now this bromine can attach itself to this electron. So what we have now is this. You have like a CH3 to make it more obvious, plus a bromine radical, okay? So that's a bromine radical, looks like BV, so it's BR actually. So that corresponds to answer choice 2, or B. Right here, this is wrong because that is a primary radical. They're saying that my radical was right here on this carbon. That's primary, not good, okay? Not good at all, it's bad. And 2 is correct, 3 is wrong. This is a secondary spot. That's bad. So let's say primary, that's secondary. Okay. What happened to your methyl? Where's your CH3? What happened? You know, we should still have the original components, right? We're not eliminating anything. This is not E2, E1. We should still have our methyl, okay? So, you know, that's bad. It actually deleted a methyl. This is a secondary spot again. And that's bad. So just knowing that trend right here will save you a lot of steps, all right? So you could have done the arrow pushing or not. Just know that we want the tertiary radical, and then we're going to replace that radical with a bromine, okay? You should not have 2 bromines. You should only have 1 bromine on that molecule. So the answer is B. All right, same thing for this question as question 7. Monobromation, that means that 1 bromine, okay, so your answer should have 1 bromine. That's what mono means. And the following alkane, using Br2 with light, would give what? What would it give me? Okay, well, it's a pretty straightforward question. This carbon right here has 1, 2, 3, 4 bonds. Okay, it has 4 bonds. That means that I cannot, I repeat, I cannot have a radical next to that carbon. Why? Well, if I did, let's say I put it right here, that means that this carbon has 5 things, right? It has 2, 4, 6, 8 electrons already, so it's happy, but then you're giving it an extra electron. So you're saying that this carbon has 9 electrons. Can that be possible? No, because that would be violating the octet rule. Okay, carbon wants 8 electrons or 4 bonds, right? So if I put a electron next to a carbon that already has 4 bonds, that's illegal, okay? So that's not good. Instead, I'm going to put this radical in a tertiary spot, okay? So this is secondary, 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 etc., right? The only tertiary spot that I can give is this location, okay? Because this carbon is attached, you know, that carbon is attached to 1, 2, 3 other carbons. And that means that it would be a good tertiary radical spot, okay? All right, so we replaced a radical with what? A bromine. Okay, so that should be my answer. It should be number 3. 3 would be good. C is correct. Right here on number 1, what happened to your methyl? Again, we're not deleting anything, so that's wrong. This is a secondary spot. That's also wrong. Another secondary spot. Also wrong. And yet another secondary spot. Also wrong. Most of these questions are just going to be asking you, hey, do you know if we should put the bromine on the allylic carbon? Do you know if we should put on the secondary one? Or should we put on the third one, the tertiary? Well, obviously you're going to say allylic, right? So it's not too bad. I don't think he's going to be asking for the reaction mechanism per se, but it's just really conceptual trends, really. Which hydrogen would be abstracted? Abstracted just means which one is going to be taken off to give a radical, okay? So give radical. First, when monobromating, that means that we put in one bromine, we just put in one bromine with Br2 and light. Okay, so which one is going to be? Well, if this confuses you, like it kind of confuses me, you just write out the line structure, okay? Write out the line structure. So we have carbon, peak, another peak, this guy, and that guy, okay? So we have this, we have that, and it seems that we have something like this. Okay, ooh, that's a bit large. So which location is it going to be? Well, automatically I know that this right here is bad, okay? So if I have a radical over here, that's pretty bad because it's just a primary. It's located on one carbon, so that's a primary. So HD is not going to work out, okay? Because that would give me a primary radical, all right? So D is wrong. All right, what if I put it here? Well, this is also a primary radical. It's attached to this carbon, okay? It's kind of like, remember nomenclature? When you're naming, when you're categorizing alcohols? Well, you don't look at, oh, well, you know, this carbon is attached to like 4 other carbons. No, you look at the immediate carbon, right? So this carbon right here is attached to one carbon, all right? It's attached to one carbon. So this radical is attached to one carbon. Okay, so that must mean that this is a primary radical and it's bad. Okay, it's garbage. So HA is incorrect. Okay, so these are the easy ones. Now, what if I put it here? Well, this is not possible because this carbon has 4 bonds already. 1, 2, 3, and 4 bonds. Right, so that's not possible. That's not an answer choice. Okay, what about HC? Well, HC right here means that I put a radical over there. So this carbon is attached to 1, 2 carbons. That's a secondary one. That's not really that good. Okay, so HC is not going to happen either. So HC is wrong. What about HE? Well, again, that's a primary. You see? Primary. So that's bad too. HB would be the correct one. Why? Well, if we put a radical over here, this carbon is attached to 1, 2, 3 other carbons, and that gives me a tertiary radical. And you know what? Tertiary radicals are pretty good. They're pretty delicious. All right? They're probably poisonous, but they're good. It's B. That gives me a tertiary radical. So the tip was, if you're not comfortable looking at all these hydrogens, just draw out the line structure and then work like that, okay? Because sometimes the hydrogens kind of, they mess up your view. So I understand that. What would be the major product for the following reaction sequence? Okay, so this is a multi-step reaction. So step 1 is asking, where am I going to put my bromine? Well, I'm going to put it in the tertiary carbon. That's going to be in this location because that carbon is attached to 1, 2, 3 other carbons, and that's really good. Okay, so I put my radical over here. The bromines break. Right there. He connects, and we get this. Okay, so that was step 1. Step 2 says that we're going to do some other reaction. So this is 2 carbons. That means it's ethyl, but then it has an alcohol. So it's ethanol, okay? So on the exam, if you see that, you can quickly convert it to the words, right? So ETOH, and we have heat. Okay, well, ETOH, well, is there any metals? Are there any metals? No. Is there a negative charge? No. So that must mean that SN2E2 is not possible. It means that SN1E1 is possible, but notice that we're adding heat. So between SN1 and E1, I'm going to pick E1, all right? And E1 has rearrangement. It has rearrangement. So automatically I know that this has rearrangement, so we can have rearrange. And it could follow Zaitsev rule, right? Because ETOH is very small. And I could do rearrangement. I could also do Zaitsev rule, right? So SN1 is not correct. We're going to be doing an E1 reaction. So automatically these two are incorrect. Now it's between Zaitsev and Hofmann. This is a Hofmann because we have a terminal alkane, or I'm sorry, terminal alkene. And this is Zaitsev because that's an internal alkene. It is also the most substituted. Notice 1 bond, 2 bonds, 3 bonds. That's tertiary, or I should say tri-substituted, sorry. And this one is 1, 2. That is di-substituted. So the more substitutes, or the higher the number, the better the product, right? And so the answer should be E5, right? So if you want to see this breaks down. There's a carbocation, but notice this carbocation is a tertiary carbocation. So we're not going to be doing any rearrangement. You only do a rearrangement when you have a secondary, and there's a possibility that you could do a tertiary. And now this is Zaitsev, and boom, there you go. So it should be 5, right? So it's the same thing as number 10, but with a different twist at the end. Again, we want to have bromine and HV. So notice HV means that we're reacting with light, and that means that we're doing a radical reaction, okay? If you don't have HV, then you're just doing a simple bromation, okay? Where you follow Markovnikov and you do all that kind of jazz. But since we're reacting with HV, which is light, we're going to be doing a radical reaction. And again, with radical reactions, we're going to put it in a tertiary carbon. Okay, so now I'm going to put my radical right there. We react. I got Br. Okay, so now we're reacting with ETOH, but this time we don't have any heat. Okay, so because we don't have a metal, and because we don't physically see a negative sign, we either do SN1 or we can do E1. But we don't have any heat, so E1 is not an option. Instead, we do SN1, where we have a substitution reaction. Okay, so what happens is that this bromine comes off, makes a positive carbocation. The ethyl is attracted right? Oop. He's attracted. He goes there. And then he makes an oxygen with hydrogen. And then let's see, CH2, CH3. And then the hydrogen leaves and it gives us this guy. CH2, CH3. Alright, so what should be your answer? Notice that we did an S and 1, so our double bonds should not be there. 1 is wrong, 5 is wrong. Okay. Alright. Now it's a matter of preference, right? Well, not preference, but location. So this is wrong. Like, what happened? What? Like, why is it over here? Why did he use a primary radical, right? You put a radical right there, that's not good, okay? That's pretty bad. So that's a primary reaction. Okay. Over here, again, that is a primary reaction. You put it like the radical over there, or it could be there, it doesn't matter. That's not good. This is a primary reaction. So that's bad. 4 is bad. Okay, what about 3? Well, 3 looks weird, but it's the same thing, okay? It's the same thing. They just did this. Okay? They kind of like slanted it a little bit and then put the oxygen, CH2, CH3. Okay, so this guy just kind of like slanted over and made room for the oxygen. It's kind of weird, but it's the way they drew it. So C is correct. C. What would be the major product for the following reaction sequence? Again, we're doing a radical reaction because we have HV. Always make sure that you're reacting with light. Okay, that's a dead giveaway that you're doing a radical reaction. So that must mean that I'm going to be doing a tertiary radical right there. And that must mean that I have a bromine right there. Okay, let's do it over here. So that radical became a bromine. Okay. Now in step 2, we have I'll never pronounce that correctly. Let's just say T-butyl oxide, hydroxide, sorry. Yeah. Okay, so that means that we have a metal over here and we're essentially strong. Because we have a metal, we're strong, okay? Metals are like sodium, potassium, lithium. That's what you're really working with in this class. And this is pretty iconic, okay? It's pretty iconic. Automatically, I know that this is going to be what? E2 reaction. It's E2 reaction because it's strong. Notice the metal. And there's heat, okay? Now, is it Zaitsev or Hofmann? Well, it's going to be Hofmann because you're working with T-butyl. Anything that's T-butyl, again, for like the last time, anything that is T-butyl is automatically Hofmann. Right. So Hofmann means that I'm going to be expecting the worst possible product. I should be expecting a terminal alkene, okay? Not internal. So this is a SN2 reaction. This is also SN2 because you added something that wasn't a double bond. That's bad. You're expecting a double bond. So 2, 4, and 5 are wrong. And the double bond that you should be expecting, right, is what? A terminal alkene. It should be outside. It should only have 2 substitutions. 1, 2 substitutions right there. So this one has 1, 2. That's good. This one has 1, 2, 3. And 3 is better than 2, but we want the worst product because this is Hofmann. So 1 is wrong, but 2 is correct. Or, yeah, 3 is correct. Sorry. So C would be the correct answer. And it just came back to Zaitsev versus Hofmann. Should be expecting a Hofmann reaction. Right? Awesome. which free radical is the most stable? Well, automatically you're thinking, hey, E looks pretty good. E looks really good. You know, that's a tertiary. We'll get back to that one. This is a primary. This is also primary because it's connected to one carbon. So that's a primary. This is a secondary. And this is also what? You're thinking secondary. Okay. So the primary ones should be out. The secondary one should be out as well. But before you get rid of A, look very, very closely. Notice that you have a double bond. Okay, who cares? But this radical is on the carbon next to the double bond. So that means, again, remember the allylic. If you have a double bond right there, and we have a radical next to it, that's pretty good. That's like the best one. This is allylic. Okay? That's allylic. And so this one is actually more stable. Most stable. Question mark? Like, yeah, it is, actually. So, it's the most stable. It's better than a tertiary. So this is better. This is better than a tertiary. So if A was something else that was like a secondary, then E would be right. But because A is allylic, it's going to be the best one. It's better than E. And so your answer should actually be A. Should be A. Because this is allylic. Allylic is more stable than a tertiary. Allylic just means that this carbon that's next to the double bond is stable. It's like the best carbon. Okay? So just keep that in mind. Okay, which of the following is a major product for the following reaction sequence? NBS with light. My gosh, what is NBS? Well, NBS, don't worry about it. Just know that NBS, let's do it, NBS gives 1 Br, okay? So instead of NBS, erase it and put Br2, okay? Just ignore it, okay? You're not going to be using it in real life, I guess, if you're just taking organic chemistry just to take it. Just ignore NBS and put Br. And then instead of light, put HV. And then continue as normal. Alright. So I'm reacting Br. Well, I can't do anything here because, well, it doesn't make any sense, right? These are double bonds. If I put a Br there, if I put a radical, I'm going to get a secondary radical, and that's not good, okay? So instead, I'm going to be putting it over here because I would get a tertiary radical. So I'm going to be having a bromine over here. And step 1 is complete. Step 2, I'm reacting with sodium methoxide, right? If you're not comfortable with Me, you could just say CH3O negative, right? And that's already strong because we have a metal. We have sodium, so it's strong. Okay, so that gives us into SN2E2 world. But notice that I have heat. It's also triangle. Well, the heat separates me. It tells me that I'm going to be doing an E2 reaction. Okay, so I'm going to be doing E2 reaction. There's no rearrangement. No rearrangement. Okay, and because because we are reacting with methyl, right? Is just very small. Is going to be Zysov because this compound is very small, the sodium methoxide. Okay, so that must mean I have something internal. Well, if I have something that's internal, I don't want a terminal alkene, so that's wrong. All right, over here, this is impossible. This carbon has, let's see, 1, 2, 3, 4, 5 bonds. Is that possible? No, that's pretty disgusting. That carbon has 5 bonds. Carbon has 5 bonds. That's bad. It's wrong automatically. So it should be 2. Because this is Zysov. It eliminated the bromine via E2 reaction and just put a double bond. This double bond is tri-substituted, so that's 1, 2, and 3, right? So that is a tri-substituted compound, and it should be the correct answer. So your answer should be B, right? So again, NBS just gives you 1 Br, okay? And we want the tertiary radical. We're doing an E2 reaction, that's Zysov, there's no rearrangement, and it should be 2. What would be the major product for the following reaction? We're reacting this molecule with HBr, but the twist is that we have peroxide. Well, peroxide actually does a reaction that is a radical, right? So again, since we're reacting with a peroxide, which has the formula ROOR, okay, it means that we're going to be doing Anti-Markovnikov, anti-mark, okay? So it's anti-mark, and let's do it over here. This right here has 1 hydrogen, and this one has no hydrogens, okay? Well, that means that instead I'm going to be putting my bromine, in the area with the most hydrogens, okay? So there we go. Why? Well, for Anti-Markovnikov, all you need to know is that the hydrogen goes in the location with the least amount of hydrogens, okay? So we want our little hydrogen to be antisocial. We don't want him to have too many friends for Anti-Markovnikov. For Markovnikov, which is just standard, we want hydrogen, or whatever is the positive part of the molecule, to have the most friends. So for instance, if I had X and Y, and X was positive, well, this positive X is going to be in the location of the most hydrogens, okay? So that's just kind of like a quick rundown of Markovnikov. So that was it. The answer should be 1, right? Should be 1. This followed Markovnikov. That's wrong. You did like a SN2 reaction right there. That's super wrong. Actually, this is SN1 reaction. That's wrong. I don't know what happened there. You had like a secondary radical formation. That's wrong. Okay. Over here, why do you have a double bond, right? You should have eliminated the double bond. So 5 is wrong. It should be A. Now we have HBr with peroxide and light. So this means that it's a radical because of HV. We are doing Anti-Markovnikov because of the peroxide. So it's anti-mark. So let's do anti-mark in the first step. Over here, this location has no hydrogens. This location has 1 hydrogen. So I'm going to put the new one over here, okay? And my H, my turquoise H, is going to be the Br, okay? All right, so here's what we have now. We have this. For Anti-Markovnikov, the added H will be in this location, and the added Br will be in this location, right? Normally we ignore the red H, okay? We typically ignore it. I just want you to show, I just want to show you the hydrogen. All right, now step 1 has finished. We are now reacting with dimethyl sulfoxide, which is aprotic, and also sodium nitrate, or nitrite, something. Anyways, because it's aprotic and there's no heat, it's not going to be E2. Okay, we have a metal, so it's going to be SN2. Okay, so SN2 means that this bromine comes off. It reacts with sodium nitrate or nitrite, whatever that is, and we just have N3. Not too bad, right? So this is wrong. What happened to your methyl? Wrong. Why do you have a double bond? That's wrong. Why are you doing solvolysis? You shouldn't have your solvent attached. That's wrong. Okay? This is Markovnikov. you basically ignored your peroxide. That's wrong. Okay, so it should be 2. B. What would be the major product for the following reaction sequence? Right, so again, this is E2 reaction because we have heat, we have a metal, and it's a big bulky base. Okay, so it's E2 reaction, means no rearrangement, and it should be Hofmann because it's a T-butyl. So let's draw this out. This chlorine breaks, and it gives me something like this. Right? And we want a Hofmann, so it's going to give me something bad, like that one. So that was step 2. That was step 1. Now we move on to step 2. Okay? Well, we're reacting this via a radical formation with peroxide. So the peroxide shows me that I'm Anti-Markovnikov. This shows me that this is a radical, right? And so we're going to be reacting with the double bond. So since it's anti-Mark, this one has 2 hydrogens on it. Ooh, that's a pretty bad hydrogen, actually. Okay, so anti-Mark says that my added H is going to go in the location where it has the least amount of friends. So this carbon has no hydrogens. That must mean that my product is going to look like this. Right? And let's put my Br over here. All right. So that should be it, right? Okay, so why is my bromine on that carbon? That doesn't make any sense. 5 is wrong. Okay, why is my bromine in the center carbon? That's Markovnikov addition. We want anti-Markovnikov, so this is Mark. So that's wrong. Why do we have 2 bromines? That doesn't make any sense. We don't even have 2 bromines right there. Wrong. What happened to this guy? We didn't even touch him. So, like, why is that reacting? That doesn't make any sense. 2 is wrong. Now, 1 shows me Anti-Markovnikov. This guy stayed the same. And we're looking pretty good. So this is going to be the correct answer. Should be A. 18. Carbocations are not intermediates in which of the following reactions. So HBr, that's your picture boy. You know, that's like the poster child of carbocations. So that's carbocation. So this is wrong. H2SO4, well, that's an acid reaction. And you should know that acid reactions, they always do carbocations. They can do rearrangement. So anything that could do rearrangement goes through a carbocation. So we can do rearrangement right here. We could do rearrangement over there, right? Again, that's just H2SO4. We could do rearrangement. So this is wrong. That's wrong. Now, you're probably saying, oh, well, this could do rearrangement. That's true, but notice that we're reacting with peroxide, and peroxide shoots out a radical. It's important for you to know that radicals, they don't do rearrangement, okay? You don't do rearrangement for radicals. So, radicals don't do rearrangement, okay? So C is going to be the correct answer, right? So, good. Now we go into the multi-step reaction synthesis, which is actually my favorite question. These are my favorite questions by far. Really fun. It's like playing with a puzzle piece, right? And so I like puzzles, right? Okay, so we're starting with this reaction, and we're going to be doing a radical reaction because we have HV, which it tells me that we're doing something with light, and that means that it's a radical. So automatically, I should be forming a tertiary radical. Okay. So here's my radical. It's then replaced with 1 bromine right there. Okay, so that's done. We now move on to the second one. And it shows me that we're going to do a very strong base, right? Because it has metal, It's also big and bulky because it's T-butyl. There's heat, so that's going to be E2 reaction favoring a Hofmann. So let's do that in a different color. Okay. So he pops off, and we form a Hofmann reaction right there. Okay. So after that's done, we do a BH3 in peroxide. Again, that's ROO R. So that must mean that we have hydrogen, OO, hydrogen. Notice that there are two hydrogens, there are two hydrogens, there are two oxygens, there are two oxygens. That's a peroxide. Okay. So BH3, which is a hydroboration with peroxide, I know that BH3 is going to pop off and give me an hydroxide, okay? So we should be expecting a hydroxide via anti-Mark. So this is anti-Mark, and then OH. We should have an OH. Okay, so let's do this. Well, let's do a nice turquoise. So this one has two hydrogens coming out. This only has no hydrogen coming out, okay? So anti-Mark says that I'm going to do what? What am I going to do? Well, I'm going to put the hydrogen where he has the least amount of friends. So that means I'm going to put my hydrogen right there. Okay, let's put him there. And we're going to eliminate this double bond as well. Okay? Let's get rid of that. So we have hydrogen coming out, and then we have our added hydroxide over here. Okay? And so that should be your answer. Why do you have two hydroxides? That's wrong. Why is your hydroxide not over here? That's also wrong. Why did this go by Markovnikov? Well, that's not even Markovnikov because it should be in this region. So that's not right either. This is Markovnikov. We want anti-Markovnikov because we have peroxide. That's wrong. This is the correct answer. It follows anti-Markovnikov. You have the alcohol on the very end, right? And that should be right. That should be A. So just go, like, whenever you're doing these types of questions, just kind of break it down into segments, okay? First, do your radical reaction. Then do an E2 Hofmann elimination. And then after that, do a anti-Markovnikov alcohol addition, right? Hydroboration. Not too bad, pretty simple. The last one says we have hydrogen and palladium. Well, hydrogen and palladium, that just removes a double bond. So we should have a single bond at first. Cyclopentane. Okay, so that was step 1. Step 2 says that we're going to be doing a radical reaction because we have light and bromine. Whoa, that was crazy. Silly. Okay, that was awesome though, pretty cool. So we're going to have a radical reaction, and that radical becomes a bromine. Okay, so that was step 2. Step 3 says that we're going to take out that bromine. How are we going to do it? Well, CH3OH, that just means that we have MEOH. So that's methoxide. Okay, or actually methanol. So methanol is weak because you don't have a metal. You don't have a negative sign. Okay, so that's SN1E1. But notice that we're reacting with heat. So I'm going to pick E1. Okay, so this guy pops off. What do we have? Since this is an E1 reaction, methanol comes in. We have OH and then that, right? Well, he breaks off. And we should just have an ether, okay? So that should be your answer. You should not have a double bond, okay? You should not have a double bond. Wait, actually you should. What am I doing? I did an SN1 reaction. Oh my gosh. Shame. Be disowned. Oh my gosh. That's ridiculous. Okay, so it's late, dude. Okay, my bad. So that bromine pops off, and instead we should be having a Zaitsev. What was I thinking? adhesive, you know, right? And it should be, it doesn't matter really, it could be here or it should be here. It doesn't matter, okay? What I know is that it's not going to be that one because that's Hofmann, so that's wrong, okay? So this is Hofmann, that's wrong. You have a bromine in that guy, that's super wrong. Right here, that's a SN1 reaction, that's bad. This is E1 reaction, which is good. I don't know what they did over there, that's bad. So it should be D. So that was all for this chapter. That was just radicals, and it's really simple, not too much to know, not too much to memorize. I hope that you can forgive me for that fumble, right, and some technical difficulties. Sorry about that, I really am. I hope that you do well in your exams, and I'm really proud of you for making it this far in Ochem. And I hope that you continue to study and to learn, and remember that I love you. So again, thank you for watching, and I hope that you have a wonderful, wonderful day and life. Love you. Goodbye.